The shape of the universe. Look up at the night sky and imagine this quiet question. If you could travel forever in one straight line, would you reach an edge, or would you gently circle back to where you began? Tonight, we softly explore the shape of everything. Before we begin, I'd love to know where in the world you're listening from, and if calm journeys through space help you relax or drift to sleep, you can subscribe and join us again under the stars. When we talk about the shape of the universe, we are asking one of the biggest and quietest questions humans have ever wondered. What does everything look like all together? Not just Earth, not just our sun, not even just our galaxy, but all of it. Every star, every galaxy, every tiny spark of light spread across the dark. Long ago, people believed the universe was small and simple. In ancient Greece, thinkers imagined a perfect set of crystal spheres holding the stars. The Earth, they thought, rested safely in the centre. It felt neat, it felt complete, and for a long time it felt true. But over centuries, careful observers began to notice something strange. The planets did not move in perfect circles the way they were supposed to. Their paths wandered, they looped, they behaved in ways that did not fit inside crystal shells. Then came new ideas, new tools. Telescopes turned toward the sky. In the early 1600s, pointed a small telescope upward and saw mountains on the moon and moons around Jupiter. Suddenly, Earth was no longer the quiet centre of everything. The universe felt larger, more open, less certain. Still, even then, most people believed the universe had a simple shape. Many thought it was flat and endless, like an infinite sheet stretching in all directions. If you travelled far enough, you would just keep going forever. But in the early 1900s, a quiet revolution changed everything. A man named looked at gravity in a completely new way. Before him, scientists described gravity as a force pulling objects toward each other. Apples fall, planets orbit. It seemed simple. Einstein said something softer and stranger. He said gravity is not just a pull, it is the bending of space itself. To understand this, imagine a smooth stretched blanket. If you place a heavy ball in the centre, the blanket dips. Now, if you roll a smaller marble nearby, it curves toward the heavy ball, not because the ball is grabbing it, but because the surface beneath it is bent. Einstein realized that space and time together form a kind of fabric. Scientists call it space-time, and massive objects like stars and galaxies bend this fabric. This idea came from his great work called the E.O., published in 1915. In it, he showed that the universe itself could have a shape that curves. This was a stunning thought. If space can bend, then maybe the whole universe has a large-scale shape. It might not be flat at all. To picture this, think about the surface of Earth. If you stand in a field, the ground looks flat. You can walk in a straight line and feel like you are moving across a flat plane. But Earth is actually round. It is a sphere. The curve is just too gentle to notice at first. In the same way, the universe could look flat in our small neighbourhood but still curve gently on a much larger scale. Scientists began to imagine three main possibilities. The first is a flat universe. In this case, parallel lines stay parallel forever. Light travels in straight paths across vast distances. If you drew a giant triangle between distant galaxies, the angles would add up to exactly 180 degrees, just like in school geometry. The second possibility is a closed universe. This shape is like the surface of a sphere. In a closed universe, space curves back on itself. If you travelled far enough in one direction, in theory, you might eventually return to where you started. There would be no edge, just a smooth, endless curve. The third possibility is an open universe. This shape curves the opposite way like a saddle. It bends outward. In this kind of universe, space spreads and opens more and more as you move away. But how can we test something so large? We cannot step outside the universe to look at it from far away. We are inside it. It is like trying to see the shape of a forest while standing between the trees. So scientists look for clues in light. One of the most important clues comes from something called This faint glow fills all of space. It is very old light, left over from the early universe, about 380,000 years after the beginning. That beginning is often called It was not an explosion in space, it was the rapid expansion of space itself. Everything was once hot and dense, then space stretched and cooled. The cosmic microwave background is like a baby picture of the universe. It shows tiny ripples in temperature, tiny differences that later grew into galaxies and stars. By studying the patterns in this ancient light, scientists can measure how space bends. In the early 2000s, a spacecraft called carefully mapped this glow across the sky. Later, the mission made even more detailed maps. These observations gave us one of the calmest and most surprising answers in science. On the largest scales we can measure, the universe appears very close to flat. Not perfectly flat in the way a table is flat, but flat in the way geometry describes. The angles behave as expected. Light travels as if space is not strongly curved overall. This does not mean the universe is small. A flat universe can still be infinite. It could stretch on forever, beyond what we can see. Or it could be so large that any curve is too gentle to measure. When we look into the night sky, we only see a part of the universe. Light has a speed limit. Nothing travels faster than light. So we can only see as far as light has had time to reach us since the beginning. This boundary is called the observable universe. Beyond it, space may continue. We simply do not know. Imagine standing in a quiet ocean at night with a small lantern. You can see only as far as your light reaches. Beyond that circle of glow, the ocean continues into darkness. It does not end just because you cannot see it. The same may be true of the universe. There is something deeply calming about this idea. We live on a small planet orbiting an ordinary star in the galaxy called and that galaxy is one of hundreds of billions. All of this floats in a vast cosmic web of galaxies stretching across space like threads of light. And yet, on the largest scale, the universe appears smooth and simple. The tiny ripples in the cosmic microwave background are only 1 part in 100,000, almost perfectly even. It is as if the universe began with a gentle whisper instead of chaos. Still, many mysteries remain. Some scientists wonder if the universe could be flat but still finite, wrapped in ways we cannot easily imagine. Others explore ideas that space may have more dimensions than we see, folded tightly beyond our senses. The truth is, we are still learning. Each new telescope, each new measurement, each careful equation brings us closer to understanding the shape of everything. For now, the best evidence tells us that the universe is very nearly flat, expanding steadily, stretching quietly like a calm breath in the dark. And as we lie here, drifting through space on our small turning world, we are part of that shape. We are tiny patterns in a fabric that bends and flows across unimaginable distances. The shape of the universe is not just a scientific question, it is a reminder that even in something so vast there is order, there is structure, there is quiet beauty written into the geometry of space itself. In the next section, we will gently explore what expansion really means, and how the stretching of space changes the story of shape over time. For now, let your mind drift outward. Imagine traveling in a straight line through endless stars, wondering softly whether you would ever come home again. When we say the universe is expanding, it can sound dramatic, like something rushing outward into empty space. But the truth is softer than that. The universe is not expanding into anything. Space itself is stretching. The distances between galaxies are slowly growing like tiny gaps widening in a calm and silent dance. This idea first became clear in the 1920s when an astronomer named studied distant galaxies. Using a powerful telescope, he noticed something unusual. The light from faraway galaxies was shifted toward the red end of the spectrum. This is called redshift. It happens when something moves away from us, stretching the light waves and making them longer. Hubble discovered that almost every galaxy he looked at was moving away, and the farther away a galaxy was, the faster it seemed to be receding. This simple pattern became known as it showed that the universe is not still, it is growing. To picture this, imagine small dots drawn on the surface of a balloon. As you gently blow air into it, the balloon expands. The dots move farther apart from each other. No dot is the center of the expansion. Every dot sees the others drifting away. In the same way, every galaxy sees other galaxies moving away because space itself is stretching between them. But here is something important. The galaxies are not flying through space like pieces of shrapnel. Instead, the space between them is expanding. On smaller shells, gravity holds things together. Our solar system stays bound. The Earth continues to circle the Sun. Our galaxy, the A, stays intact because gravity is strong enough to resist the gentle pull of expansion at that scale. So expansion shapes the universe on the largest distances, but locally, gravity keeps things calm and stable. Now, remember the three possible shapes we talked about earlier: flat, closed, and open. The shape of the universe is deeply connected to how it expands over time. If the universe were closed, like the surface of a sphere, gravity might one day slow the expansion and even reverse it. Everything could begin moving closer again in a slow contraction. Some once called this idea the Big Crunch, the opposite of if the universe were open, shaped like a saddle, expansion would continue forever, and galaxies would drift apart more and more quickly, thinning out into a colder and darker future. If the universe is flat, the expansion continues forever as well, but it slows in a very delicate balance. Not enough gravity to pull it back, not enough curvature to change its path dramatically, just a steady, quiet stretching across unimaginable time. For a long while, scientists believed gravity alone controlled this expansion. They thought matter, both visible and invisible, would decide the fate of everything. But in the late 1990s, something surprising appeared. Two teams of astronomers were studying distant exploding stars called supernovae. These supernovae act like cosmic candles. Because they shine with known brightness, scientists can measure how far away they are by how dim they appear. By comparing distance and redshift, they hope to measure how the expansion of the universe was slowing down. But instead of slowing, the expansion seemed to be speeding up. This was unexpected. It was as if the universe had gently pressed an invisible accelerator. To explain this, scientists revived a mysterious idea connected to Einstein's equations. They called it dark energy. We do not know exactly what dark energy is. It does not glow. It does not clump like matter. But it seems to fill space itself, pushing galaxies apart at an ever-increasing rate. Today, measurements from the mission suggest that about 70% of the universe is dark energy. About 25% is dark matter, an invisible form of matter that adds gravity but does not shine. Only about 5% is ordinary matter, the atoms that make up stars, planets, oceans, and us. This means the shape and fate of the universe are mostly guided by things we cannot directly see. Yet even in this mystery, the universe behaves with quiet consistency. When scientists map the cosmic microwave background, that ancient glow from the early universe, they find patterns that match a flat geometry with astonishing precision. It is almost as if the universe balanced itself carefully at birth, not too curved, not too chaotic, just on the edge between different possibilities. Some researchers explore whether space might have a more complex global shape. Could it wrap around like a three-dimensional version of a video game world, where travelling far enough in one direction brings you back from the opposite side? Could there be subtle patterns in the cosmic microwave background that reveal such wrapping? So far, we have not found clear evidence of this. The observable universe appears smooth and flat within very tight limits, but the part we can see is only a portion of the whole. Beyond our cosmic horizon, space may continue endlessly, or it may fold in ways too large for us to detect. We are like ants walking across a vast surface, sensing only a tiny patch beneath our feet. As the universe expands, light from distant galaxies stretches too. Over billions of years, galaxies beyond a certain distance will move away so fast that their light will never reach us again. They will fade beyond our horizon. Future observers, living trillions of years from now, may see a much darker sky. But right now, we live in a special era. The universe is old enough for galaxies and stars to form, and young enough that we can still see the ancient glow of its beginning. We can measure its shape, we can trace its expansion, we can ask questions that once seemed impossible. And all of this understanding comes from careful observation, quiet math, and patient curiosity. The shape of the universe is not something we can hold in our hands. It is something we infer from light that has travelled billions of years to reach us. It is written in faint temperature ripples and tiny shifts toward red. When you think about it, that is extraordinary. Tiny beings on a small planet can look at faint microwaves in the sky and learn about the geometry of everything. So tonight, as you rest, imagine space not as empty darkness, but as a gentle fabric stretching slowly. Imagine galaxies floating like glowing islands, drifting apart in a calm cosmic tide. The universe may be flat, it may be infinite, it may curve so softly that no edge can ever be found. But whatever its true global form, it carries us with it, quietly expanding second by second. And in that slow expansion there is no rush, only time, only space, only a vast and patient geometry unfolding in the dark. Now that we have gently explored how the universe expands, we can ask an even softer question. If space is stretching, and if its shape appears almost perfectly flat, how did it become this way in the first place? Why does the universe look so smooth and balanced across such enormous distances? When scientists study the early universe, they find something surprising. Regions of space that are now billions of light years apart look almost exactly the same in temperature and structure. The faint glow of the is nearly uniform in every direction. The differences are tiny, only small ripples in an otherwise smooth sea. But here is the puzzle. If those distant regions are so far apart today, light would not have had enough time to travel between them since the beginning. They should never have been able to exchange energy or information, and yet they appear almost identical, as if they once shared the same conditions. To solve this mystery, scientists proposed a gentle but powerful idea called cosmic inflation. In the late 1970s and early 1980s, physicists such as suggested that in the very first tiny fraction of a second after the universe expanded incredibly fast. Not just fast in the way we imagine rockets moving, but faster than we can easily picture. Space itself doubled in size again and again in a blink shorter than a blink. Before inflation, the universe may have been small enough for all its parts to share the same temperature and properties. They were in contact, they were connected. Then inflation stretched that tiny, smooth region to a size far larger than we can see today. It is a bit like drawing a small circle on a balloon before blowing it up. Once the balloon expands, that little circle becomes huge. The surface looks smooth because it was smooth before the stretching. Inflation does something else important. It makes the universe appear flat. Imagine again the surface of a sphere, like Earth. If you zoom in close enough, any small patch looks flat. Now imagine stretching that sphere to an enormous size. The curve becomes so gentle that it is almost impossible to detect. That is what inflation would do to space. It would smooth and flatten it across vast distances. This idea fits beautifully with the measurements from missions and the patterns in the cosmic microwave background match predictions from inflation very closely. Tiny fluctuations seen in that ancient light may be the stretched-out fingerprints of quantum ripples from the earliest moments. Yes, even quantum physics plays a role in the shape of the universe. In the smallest scales, reality is not perfectly still. Even empty space has tiny fluctuations. Little random changes in energy appear and disappear. During inflation, those microscopic fluctuations were stretched to cosmic size. Over billions of years, gravity amplified them. Regions slightly denser than average pulled in more matter. They grew into galaxies, clusters, and the large cosmic web we see today. So the grand structure of the universe may have begun as tiny whispers in the quantum fabric. This means the shape of the universe is not just about geometry. It is about history. It is about what happened in the first moments of time, and yet we must be honest. Inflation is a powerful idea, supported by strong evidence, but it is still a theory. Scientists continue to test it. They search for subtle patterns in the polarization of the cosmic microwave background. They build new telescopes and instruments, hoping to detect faint signals from gravitational waves produced during inflation's rapid stretch. So far we have hints, but not final proof. Still, the overall picture is calm and consistent. The universe began hot and dense, it expanded, it cooled, it formed atoms, stars and galaxies. Its large-scale geometry appears very close to flat, and its smoothness across enormous distances suggests an early period of rapid stretching. When you think about it slowly, this story feels almost peaceful. The universe did not grow unevenly or chaotically. It seems to have followed simple mathematical rules. It evolved step by step, guided by gravity, energy, and the properties of space itself. The fact that we can describe this story using equations is remarkable. The laws that shape the motion of planets also shape the expansion of galaxies. The same gravity that pulls an apple downward also curves space-time across billions of light years. And yet, there is still so much we do not know. We do not know the true nature of dark energy. We do not know whether inflation came from a deeper law of physics. We do not know if the universe is truly infinite or simply far larger than we can observe. Some scientists even explore ideas of a multiverse, where our universe is just one region among many, each with its own shape and properties. These ideas remain speculative, and evidence is still uncertain. But they remind us that our cosmic horizon may not be the final boundary of reality. For now, the most careful measurements tell us this. The universe is about 13.8 billion years old. It is expanding. Its geometry appears flat within a tiny margin of error. and its large-scale structure grew from small early ripples. This is not just a collection of facts, it is a quiet portrait of everything. As you breathe slowly and let your thoughts drift, imagine the early universe as a tiny glowing seed. Imagine it stretching rapidly, smoothing itself out, becoming vast beyond measure. Imagine small quantum ripples growing patiently into galaxies full of stars. We are part of that unfolding shape. The atoms in our bodies were forged inside ancient stars. Those stars formed in galaxies shaped by gravity. Those galaxies emerged from fluctuations written into the fabric of space almost at the beginning of time. The shape of the universe is not separate from us. We are woven into it. And as space continues to expand, carrying galaxies farther apart, the overall geometry remains calm and steady, nearly flat, nearly balanced, quietly stretching into the future. In the next section, we will explore how scientists measure curvature with even greater precision and what the future of expansion may mean for the ultimate shape of everything. For now, let the thoughts settle gently. The universe may be vast beyond imagination, but its story flows slowly, step by step, guided by simple laws and silent geometry across the dark. To understand the shape of the universe more deeply, scientists must measure something that feels almost impossible to measure. They must test the geometry of space itself, not in a small room, not across a city, but across billions of light years. One way they do this is by studying very large cosmic patterns. When galaxies formed, they did not scatter randomly. In the early universe, sound waves moved through the hot plasma that filled space. These waves left faint imprints in how matter later gathered. Scientists call these patterns baryon acoustic oscillations. They are like frozen echoes from a time when the universe was only a few 100,000 years old. By measuring the size of these patterns across different distances, astronomers can see how space has stretched over time. If space were strongly curved, those patterns would appear distorted. But again and again, observations show something steady and simple. The large-scale structure matches what we expect from a nearly flat universe. Another method uses gravitational lensing. According to the E, massive objects bend space-time. When light from a distant galaxy passes near a cluster of galaxies, its path curves slightly. This can stretch or magnify the background light, like looking through a gentle cosmic lens. By studying how often and how strongly this bending happens, scientists can learn about the total amount of matter in the universe, including dark matter. That matter influences curvature. So far, these measurements continue to agree with a universe that is remarkably close to flat on the largest scales. There is also the question of how fast the universe is expanding today. This rate is called the Hubble constant. Named after, scientists measure it in different ways. Some use distant supernovae, others use the cosmic microwave background and early universe physics. Interestingly, these two methods give slightly different answers. This difference is called the Hubble tension. It is small, but it matters. It may point to subtle physics we do not yet understand. Perhaps dark energy changes over time. Perhaps new particles exist. Or perhaps there are small measurement errors we have not found yet. Even in a universe that appears calm and balanced, there are still gentle mysteries waiting to be solved. Now let us imagine the far future. If dark energy continues to drive accelerated expansion, galaxies will drift farther and farther apart. Over billions and trillions of years, distant galaxies will move beyond our observable horizon. Their light will stretch so much that it fades into darkness. Eventually, observers in the distant future might see only their own local group of galaxies, bound together by gravity. The sky would look emptier than it does now. Stars will also slowly exhaust their fuel. galaxies will grow dimmer. Black holes will remain as quiet, heavy anchors in space, and expansion will continue, stretching the fabric of the cosmos ever wider. In a flat universe with dark energy, this expansion does not stop. It continues forever, though the details depend on the exact nature of dark energy. Some theories suggest it will remain constant. Others imagine it could grow stronger or weaker over time. If it grows stronger, there is a possibility called the Big Rip, where expansion eventually becomes so intense that it tears apart galaxies, stars, planets, and even atoms. But this idea depends on specific properties of dark energy that we have not observed. Right now, the simplest explanation is that expansion will continue gently, steadily, without such dramatic endings. So the universe may grow colder and darker, but not violently torn apart, just stretched, quietly and endlessly. Through all of this, the geometry of space remains deeply connected to energy and matter. Einstein's equations show that the shape of the universe is not chosen at random. It responds to what fills it. Matter tells space how to curve. Space tells matter how to move. This simple idea has guided a century of discovery, and yet there is something beautifully humbling about our position. We can measure curvature to within a tiny fractions of a percent. We can trace the history of expansion back nearly to the beginning, but we cannot see beyond the observable horizon. We cannot step outside space to look at its full form. It is possible that the universe extends infinitely in all directions. In that case, somewhere far beyond what we can ever reach, there may be regions that look similar to ours simply because in an infinite space, patterns eventually repeat. Or perhaps the universe is finite but unbounded, like the surface of a sphere in higher dimensions. In such a case, there would be no edge to fall off. You could travel forever without encountering a wall. Both ideas are consistent with current evidence, as long as curvature remains extremely small. When we think about shape, we often imagine edges and boundaries, but the universe may not have edges at all. It may simply be a continuous expanse of space-time shaped by its contents and history. As you lie quietly and let your breathing slow, picture space as a vast ocean, not chaotic but gently moving. Galaxies float like distant lanterns. The fabric beneath them stretches slowly, guided by invisible energy. The shape of the universe is not sharp or rigid. It is dynamic. It evolves as expansion continues. Its curvature is tied to density, to dark energy, to the balance of forces that began long ago. And somehow, in this enormous structure, there is room for small worlds, quiet nights, and curious minds. We are able to ask about the geometry of everything because the laws of physics are consistent. Light travels in predictable ways. Gravity follows elegant equations. Ancient radiation still whispers across the sky. The story is not finished. New telescopes will measure the cosmic microwave background with greater sensitivity. Large surveys will map millions more galaxies. Physicists will refine their models of dark energy and early inflation. Perhaps one day we will know with even greater certainty whether the universe is truly infinite or simply vast beyond imagination. For now, the evidence tells us this. The universe appears nearly flat. It is expanding at an accelerating rate. Its large-scale structure grew from tiny early fluctuations, and its future is likely one of continued gentle stretching. That is the quiet shape of everything we know. As this chapter closes, let your thoughts drift outward once more. Imagine travelling across billions of light years, watching galaxies slowly recede. Imagine tracing faint microwave light back to the earliest glow. The universe does not rush. It unfolds across immense time, guided by simple geometry and subtle forces. And in that unfolding there is a calm rhythm, a steady expansion, a nearly flat horizon stretching beyond sight. In the next chapter, we will explore how different shapes would change the paths of light and the meaning of distance itself. For now, rest inside the vastness. Let the fabric of space stretch softly around you, carrying stars, galaxies, and your own quiet awareness through the dark. Now let us gently explore something even more subtle. If the universe has a shape, that shape does not only decide how it looks from far away, it also changes how light travels, how distances are measured, and how time itself unfolds across space. Imagine shining a flashlight in a perfectly straight hallway. The beam moves forward in a straight line. In flat space, light behaves like that. It follows the shortest path between 2 points, and parallel beams never meet. But if space is curved even slightly, the path of light changes. On the surface of Earth, which is curved, 2 lines that begin parallel at the equator can slowly come together at the poles. This happens because the surface is not flat. In a similar way, if the universe was strongly curved on large scales, beams of light travelling across billions of light years would bend in ways that change what we see. This bending is not the same as gravitational lensing caused by a galaxy or cluster. That bending comes from local mass. Here we are talking about the overall geometry of space itself. Scientists test this idea by observing very distant galaxies in the cosmic microwave background. If space were positively curved like a sphere, distant objects would appear slightly larger than expected. If space were negatively curved like a saddle, distant objects would appear slightly smaller. Careful measurements show that distant patterns match what we expect in flat geometry. The angles behave normally. The apparent sizes fit predictions from a nearly flat universe. This may sound like a small detail, but it is deeply important. It means the rules of geometry we learn in school, that the angles of a triangle add up to 180 degrees, still apply on the largest scales we can measure. Think about that for a moment. The same simple geometry used to draw shapes on paper describes the structure of the cosmos across billions of light years. Distance itself, however, becomes more complex in an expanding universe. When we look at a distant galaxy, we are not seeing it as it is now. We are seeing it as it was when its light began its journey. If that galaxy is 10 billion light years away, the light we see tonight left when the universe was much younger. But because space has been expanding during the light's journey, the galaxy is now much farther away than 10 billion light years. So what is its true distance? Cosmologists use several definitions of distance. There is the distance the light has travelled. There is the current distance, accounting for expansion. There is angular distance, which relates to how large something appears in the sky. Each definition helps answer a slightly different question. In flat geometry, these distances relate to each other in specific ways. In curved geometry, those relationships would change. Again and again, when scientists plug in observational data, the numbers align with flatness. The expansion rate also affects how structures grow. In a closed universe with strong curvature, gravity would have more influence over time. Galaxies might clump more tightly, and expansion could eventually reverse. In an open universe, matter would thin out more quickly. In our universe, structure has grown steadily, but not excessively. Galaxies form clusters and filaments, creating a vast cosmic web. Between those filaments are enormous voids, regions with very few galaxies. This pattern matches predictions from a flat universe with dark matter and dark energy shaping its evolution. The cosmic web itself is breathtaking. Long strands of galaxies stretch across hundreds of millions of light years, like glowing threads woven through darkness. At the intersections of these threads lie galaxy clusters, some containing thousands of galaxies bound by gravity. This structure grew slowly over billions of years. Tiny fluctuations seen in them became seeds. Gravity amplified them. Matter flowed inward, stars ignited. All of this happened within a space that appears almost perfectly balanced in its curvature. It is natural to wonder why the curvature is so close to zero. Even a small difference in the early universe could have led to a strongly curved cosmos today. If the density of matter had been slightly higher, space might have curved back on itself. If slightly lower, it might have opened dramatically. Inflation offers one explanation, smoothing space and driving curvature toward flatness. But some scientists continue to explore whether deeper principles are at work. Perhaps certain shapes are more stable. Perhaps fundamental laws favor flatness. We do not yet know. There is also a philosophical beauty in flatness. A flat universe does not have a center. Every observer anywhere sees expansion happening around them. No location is special on the larger scale. This idea fits with what astronomers call the cosmological principle. It states that, on large scales, the universe is homogeneous and isotropic. Homogeneous means it is roughly the same everywhere. Isotropic means it looks the same in every direction. When we look deep into space, we do not see an obvious edge or preferred direction. Galaxies spread outward in all directions with similar patterns. Of course, on small scales, the universe is not smooth. There are stars, planets, black holes, and swirling clouds of gas. But zoom out far enough, and those details blur into uniformity. It is like looking at sand on a beach. Up close, each grain is unique. From far away, the beach looks smooth and even. The shape of the universe emerges only when we step back in our minds and consider the grandest scales. And yet, even if the universe is flat, that does not mean it is simple in every way. Space can be flat but still have complex topology. It could wrap around in subtle patterns like a three-dimensional version of a looping video game world. Detecting such topology would require spotting repeating patterns in distant galaxies or in the cosmic microwave background. So far, we have not seen clear evidence of this, but the search continues. As you rest and imagine light traveling across billions of years, picture it moving along gentle paths through expanding space. Picture triangles drawn between distant galaxies, their angles quietly adding up as expected. The shape of the universe is not loud or dramatic. It does not shout its geometry at us. Instead, it whispers through faint radiation, subtle redshifts, and delicate patterns in the sky. We listen carefully. We build instruments. We test ideas. And slowly, patiently, we learn that the cosmos appears balanced on a delicate edge, expanding nearly flat, structured yet smooth on the largest scales. In the next section, we will explore how observers in different eras of cosmic time might perceive this shape differently, and how the horizon of the universe shapes what can ever be known. For now, let your thoughts drift through curved possibilities and flat horizons, carried gently by light that has travelled longer than any human story. Now let us imagine something quietly profound. What if the shape of the universe depends in a gentle way on when you are alive to observe it? Right now we live about 13.8 billion years after the universe has expanded and cooled, galaxies have formed, stars have lived and died, the faint glow of the still fills the sky, like a soft afterglow from the beginning. Because we can see this ancient light, we have a powerful tool. It lets us measure curvature, density and expansion with great precision. It gives us a direct glimpse into the early universe. But this will not always be true. As expansion continues, especially with dark energy gently accelerating it, distant galaxies will move farther and farther away. Over trillions of years, many galaxies beyond our local group will slip beyond the cosmic horizon. Their light will stretch so much that it becomes undetectable. Future astronomers living in a far older universe may look into the sky and see only their own merged galaxy. They may not detect the cosmic microwave background at all, because its wavelength will have stretched far beyond what their instruments can measure. In that distant era, the universe may appear small and static. Without evidence of expansion, without distant galaxies rushing away, those observers might conclude that the cosmos is limited to what they see nearby. This idea is both humbling and beautiful. It reminds us that our current time in cosmic history is special for discovery. We live in an age where the evidence is still visible. The horizon has not yet closed in completely. The observable universe is defined by how far light has travelled since the beginning. Because light has a finite speed, we can only see a sphere around us, about 46 billion light-years in radius today. That boundary is not a wall, it is simply the limit of what light has had time to reach. Beyond it, space likely continues. Galaxies may exist there. Structures may stretch on, but we cannot see them because their light has not yet arrived, and in some cases, never will. This cosmic horizon shapes what we can know about curvature. If the universe is much larger than the observable region, its global shape might be slightly curved in ways we cannot detect. Imagine standing on a vast plain, so large that any curvature is too gentle to measure within your field of view. You would conclude the land is flat, even if far beyond sight it slowly curves. In the same way, our measurements show that space is extremely close to flat within our horizon, but we cannot fully rule out tiny curvature beyond it. There is a quiet lesson here about perspective. Knowledge depends on what can be observed. Our understanding of cosmic shape is built from light that has travelled billions of years to reach us. It is built from patterns frozen in ancient radiation. And yet, we are always inside the system we study. When we measure curvature using distant galaxies, we assume that the laws of physics are the same everywhere. So far, all evidence supports this assumption. The speed of light appears constant. Gravity behaves as described by the atoms in distant galaxies produce the same spectral lines as atoms here on Earth. This consistency allows us to extend local measurements to cosmic scales. Still, the horizon places limits on certainty. We can say the observable universe is nearly flat with very small error margins. We can say expansion is accelerating. We can describe the proportions of dark energy and dark matter with impressive precision. But whether the entire universe beyond our horizon is infinite or finite remains unknown. Some cosmologists consider that the universe might be much larger than what we see, perhaps unimaginably vast. In such a case, even if curvature exists, it could be so subtle that the total radius of curvature is far beyond our observable sphere. Others explore the idea that space might have a complex topology. It could be finite yet unbounded, like a three-dimensional torus, where travelling far enough in one direction might bring you back from another. Detecting such a structure would require spotting repeating patterns in the distribution of galaxies or in the cosmic microwave background. So far, careful searches have not revealed clear repeating patterns. The data from missions remain consistent with a simple, nearly flat geometry. As you rest and think about these possibilities, imagine floating in space without a map. You can see stars in every direction. You can measure how far away some are. You can detect faint background radiation. From these clues, you slowly infer the shape of the vast ocean around you. But the horizon always surrounds you. No matter how far you travel, there is always a limit set by time and light. In this way, the shape of the universe is both a scientific and a deeply human question. It asks how much we can know. It asks how far observation can reach. Right now, the answer is gentle and steady. All precise measurements point to a universe that is extremely close to flat, expanding faster over time, and structured by gravity and dark energy. The story is not finished. New observatories will map billions more galaxies. Future missions may measure the cosmic microwave background with even greater sensitivity. Subtle signs of curvature or new physics could still emerge. But even if the universe remains nearly flat within our view, that fact alone is extraordinary. It means the cosmos balances on a delicate line between different geometric possibilities. As this chapter draws to a close, let your thoughts drift to the edge of the observable universe. Imagine a faint boundary where the oldest visible light arrives. Beyond it lies more space, perhaps infinite, perhaps curved so gently that no instrument can detect it. We live inside a vast expanding fabric shaped by its contents and its history. We measure its angles and distances with care. We trace its story back to a hot beginning. And still, there is mystery beyond the horizon. In the next chapter, we will explore how different shapes would change the ultimate fate of the universe, and how geometry and destiny are woven together across time. For now, rest inside the present cosmic moment, a time when the sky still carries the memory of the beginning and the shape of everything can be studied in the soft glow of ancient light. The shape of the universe is not only about space, it is also about time. Geometry and destiny are woven together. The way space curves and the way it expands quietly influence what the far future may hold. Long ago, before darker energy was discovered, cosmologists believed the fate of the universe depended almost entirely on its density. If there were enough matter packed into space, gravity would eventually slow expansion and pull everything back together. If there were too little matter, expansion would continue forever. In that older picture, a closed universe, curved like the surface of a sphere, would one day stop expanding. Gravity would gently overcome motion. Galaxies would drift closer. Temperatures would rise. Over unimaginable ages, everything might collapse inward in a final contraction. An open universe, curved outward like a saddle, would expand forever. Galaxies would grow farther apart. Stars would burn out. Space would become colder and darker as matter thinned. A perfectly flat universe stood delicately between these two outcomes. Expansion would slow, but never fully stop. But then, in the late 20th century, careful observations of distant supernovae changed the story. Astronomers discovered that expansion is not slowing down. It is accelerating. Some unseen energy appears to be pushing space apart faster over time. This discovery reshaped our understanding of cosmic destiny. If dark energy remains constant, as described by a simple cosmological constant in the equations of the air, then expansion will continue accelerating forever. Even in a flat universe, this leads to a future sometimes called the heat death. Heat death does not mean flames or explosions, it means a gradual fading. Over trillions of years, stars will exhaust their fuel, white dwarfs will cool, neutron stars will drift silently. Black holes will slowly evaporate through a process predicted by quantum theory. Galaxies beyond our local group will slip beyond the horizon. The sky will grow darker. Energy will spread more evenly through space. Eventually, the universe may approach a state of maximum entropy, where no significant energy differences remain to power new stars or complex structures. This future is quiet and cold. If, however, dark energy were to change over time, other possibilities could unfold. If it grows stronger, expansion could accelerate more dramatically. In extreme scenarios, the stretching of space could overcome gravity even inside galaxies. Stars might be pulled from their orbits, planets could drift away. In the most dramatic version, even atoms could be torn apart in a distant event, sometimes called the Big Rip. Current observations do not require such an extreme future. Measurements from missions are consistent with dark energy behaving like a constant property of space itself. But the uncertainty leaves room for continued investigation. There is also the possibility that dark energy might slowly weaken. If it faded enough, gravity from matter could one day dominate again. Expansion might slow significantly, though current data suggest this is unlikely. All these outcomes connect back to geometry. The curvature of space is tied to total energy density. In the early universe, even tiny differences in density could have led to very different shapes and destinies. The fact that our universe appears so close to flat suggests a delicate balance. The density of matter and energy is extremely close to a critical value. This critical density defines the boundary between open and closed geometries. Inflation may have driven the universe towards this balance. By stretching space enormously in its earliest moments, it would have diluted any initial curvature, smoothing space toward flatness. So geometry may be the memory of those first fractions of a second. When we look at the large-scale distribution of galaxies, we see the outcome of billions of years of expansion guided by that geometry. The cosmic web stretches across space shaped by gravity and the underlying flatness that allows structures to grow in a predictable way. Even black holes, the most extreme objects we know, exist within this expanding fabric. Their intense local curvature does not change the overall flatness of the universe on the largest scales. They are deep dimples in a vast, nearly level surface. As you imagine the far future, picture galaxies slowly drifting apart like lanterns carried by a widening sea. The distances between clusters increase, light grows fainter. The cosmic background radiation stretches into longer and longer wavelengths, cooling toward absolute zero. Yet even in this fading future, the geometry remains calm. Space does not tear or buckle dramatically under current models. It stretches smoothly. There is something strangely peaceful in that image. The universe is not racing toward chaos. It is following equations that have guided it since the beginning. It is expanding steadily, shaped by energy we barely understand, yet consistent in its behavior. Of course, our understanding may deepen. New physics could change the story. Perhaps dark energy is not constant. Perhaps quantum gravity will reveal surprises about space-time itself. But based on what we measure today, the link between shape and fate appears clear. A nearly flat universe with accelerating expansion points toward endless growth in scale, even as local systems remain bound by gravity. Our own galaxy, the EL, will eventually merge with its neighbor Andromeda, forming a larger galaxy long before distant clusters disappear from view. On smaller scales, gravity continues to weave structures together, even as the larger fabric stretches. This contrast, local binding and global expansion, is one of the most beautiful aspects of cosmic geometry. The shape of the universe does not prevent stars from forming or galaxies from colliding. It sets the grand stage on which those events unfold. As this section comes to a gentle pause, reflect on how geometry and destiny are quietly linked. The angles of vast cosmic triangles, the faint ripples in ancient radiation, the acceleration of distant galaxies, all of these clues tell a single calm story. The universe appears nearly flat, It expands at an accelerating pace, and its future likely stretches onward into a cold, spacious eternity. In the next section, we will step back one final time and consider what it means for human understanding to measure the shape of everything, and how this knowledge changes the way we see our place in the cosmos. For now, rest in the thought that the vast geometry above you is steady and patient, unfolding across time far longer than any human lifetime, yet understandable through quiet observation and careful thought. As we come closer to the end of this long, gentle exploration, let us step back and think about something simple and profound. Tiny beings standing on a small planet have learned to measure the shape of the universe. That idea alone feels almost unreal. We are made of atoms forged in ancient stars. Those stars formed inside galaxies. Those galaxies grew along filaments shaped by gravity. And all of it exists within a vast fabric of space-time whose curvature we can estimate with delicate precision. When scientists say the universe is nearly flat, they are not guessing. They are combining measurements of distant supernovae, maps of the Ours, galaxy surveys stretching across billions of light years, and equations first written down in there. Each piece of evidence alone might feel uncertain, but together they form a consistent picture. Light from the early universe shows tiny fluctuations that match predictions from inflation. The distribution of galaxies follows patterns expected in flat geometry. The acceleration of expansion points toward dark energy filling space smoothly. The agreement between these independent lines of evidence is one of the quiet triumphs of modern science, and yet humility remains essential. All our measurements are limited to the observable universe. Beyond the cosmic horizon, space may continue forever, or it may curve so gently that its full shape lies beyond detection. We cannot see outside the system we inhabit. This limitation does not weaken the beauty of what we know. In fact, it deepens it. Knowledge grows within boundaries. We build understanding from the light that reaches us. It is also important to remember that flatness does not mean simplicity in every sense. The universe contains complexity beyond imagination. Black holes warp space-time intensely. Neutron stars compress matter to extreme densities. Galaxies collide and merge in dramatic events. But when we zoom out far enough, these intense local features average out. On the largest scales, the cosmos smooths into gentle uniformity. This smoothing is one of the reasons the cosmological principle works so well. The universe, when viewed across immense distances, appears homogeneous and isotropic. No preferred direction, no obvious center, no edge in sight. That absence of a center carries a quiet message. We are not located at a special geometric point in the cosmos. Every observer, anywhere in a similar galaxy, would see expansion happening around them. Every observer could measure the cosmic microwave background and find the same near-flat geometry. This universality connects distant minds that may never meet. There is also a deeper philosophical shift hidden in this understanding. For much of human history, we imagined the cosmos built around us. First Earth at the center, then the Sun, then our galaxy. Each time we learned we were part of something larger. Now, when we study the shape of the universe, we find no privileged location at all. And yet, this does not make our existence meaningless. Instead, it highlights something extraordinary. In a universe governed by consistent laws and simple geometry, complexity can arise. Stars ignite, planets form, life emerges, consciousness evolves. The same equations that describe cosmic curvature also allow stable orbits and long-lived stars. Flatness, combined with expansion and gravity, creates an environment where structure can grow over billions of years. In that sense, geometry is not cold or distant. It is part of the reason we are here to wonder about it. As the universe continues expanding, its large-scale shape will remain tied to dark energy and total density. If current models hold, space will stretch faster and faster, though never violently under the simplest assumptions. Galaxies beyond our local group will eventually vanish beyond the horizon. The night sky in the far future will look quieter than it does now. The evidence for expansion may slowly fade from view. We live at a rare moment, able to see both deep into the past and far across space. When you look up at the night sky, you are seeing geometry in action. Light travels along paths shaped by space-time. Distances grow as expansion stretches the fabric between galaxies. The faint microwave glow fills every direction, whispering about conditions nearly 14 billion years ago. All of it fits together into a picture of a universe that is astonishingly close to flat. Not perfectly flat in an absolute sense, perhaps, but flat enough that its curvature, if any exists, is smaller than we can easily measure. Flat enough that the angles of vast cosmic triangles behave as expected. Flat enough that space on the grandest scales we observe does not curl back on itself within our horizon. There is a quiet elegance in that balance. As we close this chapter, imagine drifting far above the Milky Way. Imagine seeing galaxies scattered like islands in a dark ocean. Picture the ocean itself stretching slowly outward, its surface almost perfectly level, expanding under the influence of unseen energy. You float there, not at the center, not at an edge, but simply within. The shape of the universe is not a sharp outline or a visible border. It is a property of space-time itself, measured through light, inferred through mathematics, tested through observation. And after all the measurements and equations, what remains is something softly beautiful. We live inside a vast, expanding cosmos whose geometry is calm and balanced. Its beginning left faint ripples we can still detect. Its future stretches into cold and spacious distance. Its present holds stars, planets, and curious minds asking gentle questions. The universe may be infinite. It may be finite yet unbounded. It may curve so slightly that no edge can ever be found. But tonight, as you rest, you can carry one steady thought. The fabric of everything around you is nearly flat, quietly expanding and filled with ancient light still travelling across time. And within that immense patient geometry there is room for wonder. Now, after exploring curvature, expansion and destiny, we can ask one last deep and gentle question. What does it truly mean for space itself to have a shape? When we think about shape, we usually imagine objects. A ball is round, a box has edges, a sheet of paper is flat. These are shapes we can hold and see from the outside. But the universe is not an object inside something else. It is not floating in a larger room as far as we know. The universe includes all of space and time. So when we talk about its shape, we're not describing how it looks from outside. We are describing how distances and angles behave within it. This idea can feel strange at first. To understand it, imagine a two-dimensional world living on the surface of a sphere. The beings in that world cannot see up or down. They only know forward, backward, left and right along the surface. If they measure triangles on their surface, they might discover that the angles add up to more than 180 degrees. From that simple fact, they could conclude that their world is curved, even if they cannot step outside it. In a similar way, we measure the geometry of our three-dimensional space from the inside. We look at light paths. We measure angles between distant objects. We study the patterns in them. From these clues, we infer curvature. So far, every precise measurement tells us the curvature is extremely small. Within our observable region, space behaves as if it is flat. But here is something subtle. Even if space is flat, it can still be dynamic. It can stretch. It can expand. Flatness does not mean stillness. This stretching began in the early universe and continues today. The initial burst of inflation proposed by physicists like Key would have driven curvature towards zero. Later, the steady expansion shaped by the matter and dark energy carried that flatness forward across billions of years. The result is a cosmos that appears balanced at the largest scales. There is also the idea that space and time are not separate things but woven together. In the cell, gravity is not described as a simple force pulling objects. Instead, mass and energy curve space-time, and objects move along those curves. When we speak of the shape of the universe, we are really speaking about the geometry of space-time itself. On local scales, near a planet or star, curvature can be strong. The sun curves space-time enough to guide Earth's orbit. A black hole curves space-time so intensely that not even light can escape once it passes a certain boundary. But when we zoom out to scales of hundreds of millions of light years, these local curvatures blend into an almost uniform background. The overall geometry becomes smooth and simple again. It is like looking at waves on the surface of the ocean. Up close, the water rises and falls, but from high above, the surface can appear almost flat. Another subtle point is this. The universe does not need to have an edge to have a shape. A sphere has no edge on its surface. You can walk forever without falling off. In the same way, if the universe were closed and curved back on itself, it would not require a boundary. But current evidence suggests that if curvature exists, it is extremely small. This leaves open the possibility that the universe extends infinitely. An infinite flat universe would mean space continues forever in every direction. There would be no final galaxy, no last star. Matter would continue beyond any distance we could travel. That thought can feel overwhelming, but it can also feel peaceful. Infinite space does not rush or crowd, it simply extends. There is also a mathematical beauty in flat, infinite geometry. Patterns repeat statistically. On very large scales, the distribution of matter follows simple rules. Gravity sculpts structures, but the underlying framework remains steady. Even if the universe is finite, it may be so vast that its total size lies far beyond what we can observe. Our cosmic horizon limits our knowledge, not necessarily the cosmos itself. When we measure flatness, we are measuring the ratio between total energy density and a critical value. If the density equals that critical value, space is flat. If it exceeds it, space curves positively. If it falls below, space curves negatively. Observations show the total density is astonishingly close to the critical density. This delicate balance is one of the reasons inflation became such an appealing explanation. Without inflation, maintaining such precise balance would seem unlikely. But science remains open. Future data may refine these measurements. Tiny deviations from flatness could still appear. As you imagine the shape of the universe now, try not to picture a giant object floating somewhere. Instead, picture the invisible grid of space stretching smoothly in all directions. Picture distances growing slowly between faraway galaxies. Picture light travelling along paths shaped by subtle curvature. We are inside that grid. Every atom, every breath, every thought unfolds within space-time. The shape of the universe is not separate from daily life. It determines how gravity works, how galaxies evolve, how cosmic history unfolds. And yet in everyday experience we do not notice curvature at all. Earth feels flat beneath our feet. Space feels empty above our heads. Only through careful measurement do we uncover the deeper geometry. That discovery, that simple measurements of ancient light can reveal the shape of everything, is one of humanity's quiet achievements. As this section gently closes, let your thoughts widen one more time. Imagine drawing a straight line through space and following it for billions of years. In a flat, infinite universe, you would never return to where you started. In a closed universe, you might eventually circle back. In an open universe, paths would diverge even more dramatically. But within our observable horizon, all signs point to balance, nearly flat, expanding steadily, guided by dark energy and gravity in calm partnership. In the next and final section, we will reflect on what this understanding means for our place in the cosmos, and how knowing the universe's shape changes the way we see ourselves. For now, rest inside the idea that the fabric around you, invisible, immense, and ancient, is shaped with remarkable simplicity, stretching softly through time. As we move into this final section of our exploration, it is time to reflect on what it truly means to measure the shape of the universe and what that knowledge gives us. The universe is vast beyond imagining, stretching across billions of light years in every direction, filled with galaxies, stars, and dark energy. Yet we can understand something about its very geometry from our small vantage point. That is an extraordinary gift of science and curiosity. When we study cosmic geometry, we are not just learning abstract mathematics. We are learning about the framework that governs every orbit, every collision, every pulse of light. The expansion of space, the gentle curvature, and the invisible push of dark energy combine to create a stage on which galaxies form, stars ignite, and planets like our own appear. Our existence is intimately tied to the quiet, precise balance of this cosmic shape. It is also humbling. The universe has no center. It has no preferred direction. There is no edge to fall off, no outside vantage from which to see the whole. All observations come from within, limited by the speed of light and the horizon of what we can ever detect. And yet, from this tiny corner, we can measure angles of distant triangles, detect faint radiation from the dawn of time, and infer the flatness of space with remarkable precision. This understanding changes perspective. Humans often imagine themselves at the center of events in space or time. But in the vast geometry of the cosmos, no observer is privileged. Every galaxy sees the same expansion, every observer has their own horizon, and within this shared structure, life, consciousness, and curiosity can emerge. There is a quiet poetry in this balance. The universe is not chaotic, but structured, not confined, but infinite or unbounded. Thinking about the shape of space also invites wonder about the far future. Dark energy ensures that galaxies will drift apart, stars will burn out, black holes will remain as quiet monuments in the vast fabric of space-time. Light from distant objects will stretch and fade. And yet, even as everything grows dimmer and colder, the geometry itself remains steady, flat, nearly uniform, expanding gently. It is a cosmic rhythm that carries on far longer than any human story. At the same time, the subtle mysteries remind us of the limits of knowledge. Beyond our horizon, space may continue endlessly, tiny curvature might exist undetected. Exotic topology could loop back in ways we cannot yet measure. Each unanswered question is a space for curiosity, an invitation to keep observing, measuring, and imagining. Science is both a map and a meditation. It reveals structure, but it also leaves room for awe, and perhaps that is the most beautiful part. The universe is vast, ancient, and expansive, yet it is comprehensible. We can measure its shape, understand its expansion, and glimpse the forces that govern its destiny. And in doing so, we discover something profound about our place, that within a cosmos of near infinite extent, with gentle curvature and steady expansion, there exists a small planet where life can observe, wonder, and dream. So tonight, as you rest, and picture the universe not as a distant abstract object, but as a calm living geometry. Imagine light travelling for billions of years, tracing straight and curved paths alike, whispering the story of space and time. Imagine galaxies drifting in the expanding fabric, and stars forming and fading as the rhythm of gravity and energy carries on. Imagine that within all this, you are part of a moment that can observe, measure, and reflect on the shape of everything. In the quiet of this reflection, there is a connection between the past and the present, between the observable and the hidden, between human curiosity and cosmic vastness. The nearly flat universe stretches outward, carrying every galaxy, every black hole, and every speck of matter along its gentle curves. And in the midst of this immensity, we find both knowledge and wonder, balance and mystery, calm and infinite possibility. With this, Chapter 5 closes. The story of cosmic shape, expansion, and destiny leaves us with a quiet sense of place, a gentle awareness of the universe's geometry, and a calm curiosity for the mysteries that remain. Let your thoughts drift through these gentle curves of space-time, carried softly by light that has travelled longer than any story ever told. The universe is vast, nearly flat, expanding steadily, and we are here, quietly noticing and softly dreaming alongside it.